Hello there, and welcome to Space Historians. I'm so glad you found your way here tonight. Before we begin, take a moment to get comfortable. Adjust your pillow, let your body sink into whatever surface is supporting you, and know that you're exactly where you need to be. Where in the world are you watching from? A quiet bedroom where the stars might be visible through your window? A cozy corner where the day is finally winding down? Wherever you are, you're welcome here. Tonight we're going to explore something fascinating that happened in our solar system and continues to happen. We'll talk about interstellar objects, visitors from beyond our cosmic neighbourhood, and what they tell us about the universe we inhabit. We'll discover what Oumuamua and Comet Borisov revealed, understand what Interstellar Object 3I/Atlas taught us, and contemplate what real threats might exist in the spaces between stars. But most importantly, we'll understand why the universe, despite its vastness and occasional dangers, operates on timescales that allow us to rest peacefully tonight. But don't worry, this isn't going to be a countdown of catastrophic scenarios or a catalogue of nightmares waiting in deep space. Instead, we'll move slowly and carefully through the science, the discoveries, and the beautiful mathematical certainty that governs how objects move through our corner of the galaxy. By the end, I think you'll find that understanding cosmic threats actually brings peace, because the universe follows rules, operates on schedules we can predict, and gives us plenty of time to simply exist. If you enjoy these calm explorations of space and the stories it tells, a like and subscribe really helps reach others seeking the same peaceful way to end their day. And to those already subscribed, thank you for being part of this quiet community where we can wonder together about the cosmos. So settle in. Let your shoulders drop away from your ears. Take a slow breath in through your nose and let it out gently. And let's begin our slow drift through the space between stars, where ancient objects travel for millions of years, and where the real threats teach us more about patience than panic. There's nowhere you need to be. Just listen and let the story unfold. In October of 2017, astronomers at the Pan-STARRS telescope in Hawaii noticed something unusual. An object was moving through our solar system, and its trajectory was all wrong. Not wrong in the sense of being dangerous or chaotic, but wrong in the sense that it didn't belong to our sun's family of planets, asteroids and comets. This object had come from somewhere else entirely. They named it Oumuamua, a Hawaiian word meaning scout or messenger, and it became the first confirmed interstellar object ever detected passing through our solar system. Before Oumuamua, the concept of interstellar objects was purely theoretical. Scientists knew they must exist. Mathematically, they had to exist, but we'd never actually seen one. And then suddenly, there it was, tumbling through our cosmic neighbourhood at 26 kilometres per second relative to the Sun. What made Oumuamua so clearly an interstellar visitor was its hyperbolic trajectory. Objects that belong to our solar system, whether they're planets or comets or asteroids, follow elliptical orbits around the Sun. They're bound to our star by gravity, travelling in predictable loops that bring them around again and again. But Oumuamua's path was different. It was moving too fast to be captured by the sun's gravity. It swept through our inner solar system in a graceful arc and then continued on its way, heading back out into the vast spaces between stars. The object itself was strange in other ways too. Observation suggested it was elongated, perhaps 10 times longer than it was wide, tumbling end over end as it travelled. Some scientists proposed it might be shaped like a cigar. Others like a pancake. Its surface reflected light in ways that suggested it might be rocky, or perhaps metallic, or maybe covered in some kind of organic material that had been altered by millions of years of exposure to cosmic radiation. But here's what's important to understand as you're settling in for the night. Oumuamua wasn't a threat. It passed through our solar system at a distance of about 15 million miles from Earth. That might sound close, but in astronomical terms it's an enormous distance. The Moon is only about 240,000 miles away. Oumuamua never came anywhere near threatening our planet. It was simply passing through, a messenger from another star system, here and then gone. The discovery raised immediate questions. Where had it come from? How long had it been travelling through interstellar space? And most intriguingly, how common are these visitors? If we'd just spotted the first one, how many others were out there, drifting through the darkness between stars, occasionally passing through solar systems like silent witnesses to the galaxy's slow dance? These questions would begin to find answers slowly and carefully as astronomers turn their attention to the spaces beyond our sun's gravitational embrace. To understand what interstellar objects really are and why they matter, we need to understand the space they travel through. When we look up at the night sky, we see stars scattered across the darkness, and it's easy to imagine that space is just empty void between them. But interstellar space is far more interesting than simple emptiness. The space between stars is not a perfect vacuum. It contains matter, just incredibly diffuse matter. On average, there's about 1 hydrogen atom per cubic centimetre in interstellar space. That might not sound like much, and it isn't. For comparison, the air you're breathing right now contains about 10 to the 19th power molecules per cubic centimetre. But that 1 hydrogen atom per cubic centimetre, multiplied across the immense volumes between stars, adds up to something significant. There are also trace amounts of other elements out there: helium, carbon, oxygen, nitrogen, all the building blocks of chemistry, floating in the interstellar medium. There are complex organic molecules, some of them quite large, that form in the cold darkness between stars. There are grains of dust, tiny particles that scatter starlight and create the beautiful dark clouds we can see in some regions of the Milky Way. And there's radiation, constantly streaming through space, cosmic rays from supernovae and other violent events, photons from distant stars, all of it washing through the void. Objects travelling through interstellar space are exposed to all of this for immense periods of time. An interstellar object might spend millions or even billions of years in transit between star systems. During that time, cosmic rays bombard its surface, gradually altering its chemistry. Dust grains impact it at high speeds, slowly eroding its surface or perhaps accreting onto it. The cold of space, just a few degrees above absolute zero, freezes any volatile material solid as stone. This is the environment that shaped Oumuamua before it arrived in our solar system. Whatever it looked like when it was ejected from its home star system, whether that was billions of years ago or more recently, it had been transformed by its long journey through interstellar space. Its surface had been weathered, irradiated, perhaps covered in a layer of organic material created by the interaction of cosmic rays with simpler molecules. And here's something worth contemplating as your breathing slows and deepens. The space between stars is incredibly vast. The nearest star to our Sun, Proxima Centauri, is about 4.2 light-years away. That means light, travelling at 186,000 miles per second, takes 4.2 years to make the journey. An object like Oumuamua, travelling at 26 kilometers per second, would take about 50,000 years to cover that same distance. 50,000 years. That's longer than recorded human history. That's longer than modern humans have existed as a distinct species, and yet on the timescale of the galaxy, 50,000 years is barely a moment. The Milky Way has existed for over 13 billion years. Stars have been forming, living, and dying for eons. And throughout all that time, objects have been drifting through the spaces between stars, silent travellers in an ancient ocean of darkness, witnessing the slow evolution of the galaxy itself. Now that we understand the space these objects travel through, let's think about where they come from. How does a rock or a chunk of ice end up travelling between star systems in the first place? The answer lies in the chaotic early days of planetary system formation, and in the gravitational dances that continue throughout a star system's lifetime. When a star forms from a collapsing cloud of gas and dust, it doesn't capture all of that material. Most of it ends up in a disk around the young star, and from that disk planets begin to form. Small particles stick together through electrostatic forces and gentle collisions. These grow into pebbles, then boulders, then planetesimals kilometers across, and eventually into planets. But this process is messy and violent. Planetesimals collide and shatter. Larger objects gravitationally scatter smaller ones. As planets grow, especially large planets like Jupiter or Saturn, their powerful gravity can fling smaller objects around like cosmic pinballs. Some of these objects crash into planets or the star. Some end up in stable orbits. And some get thrown out of the system entirely. This is probably how most interstellar objects begin their journeys. A small body, perhaps an asteroid or a comet, comes too close to a planet and receives what astronomers call a gravitational assist. But instead of being directed into a new orbit within the system, it gets accelerated to such high speeds that it exceeds the star system's escape velocity. It becomes unbound from its home star and begins the long journey into interstellar space. This process must be incredibly common. Every star system that forms probably ejects vast numbers of small bodies during its early, chaotic phase. Our own solar system likely expelled billions or trillions of objects in its first few 100 million years. Some of them are still out there, travelling through the galaxy, and some have probably encountered other star systems just as Oumuamua encountered ours. There's another way interstellar objects can form, though it's probably less common. When stars pass close to each other, which can happen in dense star clusters, their gravitational fields can interact and objects from one system can be transferred to another or ejected into interstellar space. When binary star systems become unstable, or when a star in a binary system explodes as a supernova, the resulting chaos can scatter objects across vast distances. And then there's the possibility, remote but fascinating, that some interstellar objects might be fragments of planets that were destroyed. If a planet is torn apart by tidal forces when it passes too close to its star, or if two planets collide catastrophically, the debris could be scattered with enough velocity to escape the system. These fragments would carry with them evidence of planetary processes, chemical signatures that could tell us about conditions on worlds we'll never visit. What this means, as you let your mind drift along with these ancient travellers, is that interstellar space is probably full of objects from every star system in the galaxy. Rocks from worlds orbiting red dwarf stars, ice from the edges of systems around sun-like stars, perhaps even fragments from planets that once supported life, carrying frozen microbes through the darkness, seeds that might someday take root in another world. The galaxy is vast, but it's also connected with these silent messengers travelling between its stars. After Oumuamua departed our solar system in early 2018, astronomers were eager to find more interstellar visitors. They didn't have to wait long. In August of 2019, an amateur astronomer named Comet Borisov, observing from his personal observatory in Crimea, discovered a comet with an unusual orbit. Follow-up observations quickly confirmed what Oumuamua had already taught us was possible. This was another interstellar object. They named it 2I/Borisov, with the 2I designation indicating it was the second confirmed interstellar object. And unlike Oumuamua, which had already been leaving the solar system when it was discovered, Comet Borisov was detected while approaching. This meant astronomers had time to study it in detail, to point multiple telescopes at it, to analyse its composition and behaviour as it swung around the sun. Comet Borisov turned out to be remarkably normal, at least by comet standards. It had a nucleus, a solid core of ice and rock, probably less than a kilometre across. As it approached the sun and warmed up, ice on its surface began to sublimate, turning directly from solid to gas, and creating a glowing coma around the nucleus. This coma was made primarily of water vapour, with traces of carbon monoxide and other volatiles. It developed a tail blown back by the solar wind, pointing away from the sun just like any comet from our own solar system. The composition of Comet Borisov was particularly interesting. Spectroscopic analysis revealed that its ice and dust were remarkably similar to comets from our own Oort cloud, that distant spherical shell of icy objects surrounding our solar system. This suggested that comet formation might be a universal process, that the icy bodies forming in the outer regions of planetary systems around other stars aren't fundamentally different from our own comets. But there were subtle differences. The ratio of carbon monoxide to water in Comet Borisov's coma was higher than in most solar system comets. This might indicate it formed in a colder region of its home system, or that its home star had a different chemical composition than our Sun. These small variations are clues about the diversity of planetary systems throughout the galaxy. Comet Borisov's visit was peaceful and brief. It reached perihelion, its closest approach to the Sun, in December of 2019, passing about twice as far from the Sun as Earth orbits. It never came particularly close to our planet. Throughout its visit, it was simply a comet doing what comets do, sublimating ice, leaving a trail of gas and dust, following the mathematical certainty of its hyperbolic trajectory through our solar system and back out into interstellar space. By mid-2020, Comet Borisov had faded from view, too distant and dim to observe any longer. It's out there now, heading back into the darkness between stars, its brief moment of warmth and activity as it passed near our Sun, already a fading memory in its long, cold journey. In a few million years, it might encounter another star system, warm up again briefly and continue on its way, or it might travel for billions of years through the void, a frozen time capsule preserving conditions from whatever star system gave it birth. And then came 3I/Atlas. In 2024, the Asteroid Terrestrial Impact Last Alert System, ATLAS for short, detected another object with an unusual trajectory. Initial observations suggested it might be another interstellar visitor. The third confirmed object from beyond our solar system. The astronomical community took notice immediately. 3I/Atlas was different from both Oumuamua and Comet Borisov in several ways. Its orbit, while hyperbolic like the others, was less extreme. It was moving more slowly relative to the Sun, which suggested it might have a trajectory that was only barely unbound from our solar system. Some initial calculations even suggested there was a small possibility it might be a very long-period comet from our own Oort cloud, rather than a true interstellar object. The object was also difficult to observe. It was relatively small and faint, and its trajectory took it through regions of the sky that were challenging for many telescopes to access. But astronomers around the world coordinated their efforts, gathering data whenever the object was visible, slowly building up a picture of what 3I/ATLAS actually was. As observations accumulated, the picture became clearer. 3I/Atlas was indeed an interstellar object, but one with a much more sedate velocity than Oumuamua. While Oumuamua had been racing through our solar system at 26 kilometers per second, 3I/Atlas was moving at perhaps 10 to 15 kilometers per second relative to the Sun. It was still fast enough to escape the Sun's gravity, but it would take considerably longer to leave our cosmic neighbourhood. The object appeared to be rocky rather than icy. Unlike Comet Borisov, it showed no signs of cometary activity as it approached the Sun. No coma formed around it, no tail developed. It simply reflected sunlight like an asteroid, a dark, inert chunk of rock tumbling through space. This suggested it might have formed closer to its home star, in a region where ice couldn't exist, or that any ice it once contained had been lost long ago during its journey through interstellar space. What made 3I/Atlas particularly interesting to scientists wasn't any threat it posed, because it posed none. Its trajectory kept it far from Earth, well beyond the orbit of Mars at its closest approach. Instead, what made it interesting was what it represented as a data point. With 3 confirmed interstellar objects detected in just 7 years, astronomers could begin to estimate how common these visitors really are. The calculations suggested something remarkable. At any given time, there are probably several interstellar objects passing through our solar system. Most of them are too small or too far away to detect with current telescopes. We only notice the ones that happen to pass relatively close to the Sun and Earth, where our most powerful observational tools are concentrated. The galaxy, it seemed, was even more interconnected than we'd imagined, with a constant traffic of objects moving between star systems, most of them never noticed by anyone. Let's talk about why 3I/ATLAS, despite being called an interstellar object which sounds somewhat dramatic, is completely harmless. Understanding this requires understanding a bit about orbital mechanics, but don't worry. We'll take it slowly, and by the end you'll understand why astronomers can know with absolute certainty whether an object poses any danger to Earth. Every object in space follows a trajectory determined by gravity and its initial velocity. It's beautifully simple physics, described by equations that Isaac Newton worked out over 300 years ago. When astronomers discover an object, they observe its position over several nights or weeks, and from those observations they can calculate its orbit with remarkable precision. For 3I/Atlas, those calculations showed an orbit that never brings it anywhere near Earth. At its closest approach to the Sun, it's perihelion. The object was still farther from the Sun than Mars orbits. Earth orbits at about 1 astronomical unit from the Sun. Mars orbits at about 1.5 astronomical units. 3I/ATLAS came nowhere close to intersecting Earth's orbital path. But even if an object crosses Earth's orbital path, that doesn't mean there's danger. Space is vast and Earth is small. Our planet is only about 12,700 kilometers in diameter. Even the Moon, orbiting at an average distance of 384,000 kilometers, represents a tiny target in the immensity of space. For an object to actually hit Earth, it needs to be at the exact same point in space as Earth at the exact same time. And the mathematics of orbital mechanics makes it straightforward to determine whether that will happen. Astronomers can calculate orbits centuries into the future with high accuracy. They account for the gravitational pull of the Sun, all the planets, even the slight pressure from solar radiation hitting the object's surface. These calculations can predict an object's position days, months, or years in advance, with precision measured in kilometers. If an object is going to hit Earth, astronomers know about it well in advance. 3I/Atlas was never going to hit Earth. Its trajectory was well defined, its path clear, and at no point in its passage through our solar system did it come anywhere near threatening our planet. The same was true for Oumuamua and Comet Borisov. These objects were visitors, passing through, following the mathematical certainty of gravity and momentum. This is worth holding in your mind as you settle deeper into rest. The universe operates according to rules. Objects don't suddenly change course. Trajectories are predictable. When an interstellar object enters our solar system, astronomers can immediately determine whether it poses any risk, and if it doesn't, they can watch it with fascination rather than fear. 3I/Atlas taught us things about the galaxy, about planetary formation around other stars, about the population of objects drifting through interstellar space. But it never threatened us. It was simply passing through. So if interstellar objects like 3I/Atlas aren't the real threat, what is? To understand cosmic threats to Earth, we need to look not at the rare visitors from other star systems, but at the much more numerous objects that belong to our own solar system. These are the asteroids and comets that share the Sun's gravitational field with us, and occasionally their orbits bring them close to Earth. Astronomers call these near-Earth objects, or NEOS. They're defined as asteroids or comets whose orbits bring them within 1.3 astronomical units of the Sun, which means they can potentially cross Earth's orbit. There are tens of thousands of known NEOs, and scientists discover more every week. Most of them are small, only a few meters or tens of meters across. But some are much larger, and it's the large ones that represent a genuine, though manageable, threat. The real danger comes from objects called potentially hazardous asteroids, or PHAs. These are NEOs larger than about 140 metres across that come within about 7.5 million kilometres of Earth's orbit. An object 140 metres across, if it hit Earth, would cause regional devastation. It wouldn't be an extinction-level event, but it would destroy a major city if it hit one, or create a tsunami if it hit the ocean. Larger objects, a kilometre across or more, are the ones that could cause global catastrophes. An impact from a kilometre-sized asteroid would throw enough dust into the atmosphere to affect global climate, potentially causing crop failures and widespread famine. These are the events that happen on timescales of hundreds of thousands or millions of years. But when they happen, they reshape life on Earth. The good news, and it is genuinely good news worth contemplating as your muscles relax and your breathing deepens, is that we're systematically cataloguing these objects. NASA and other space agencies around the world operate telescopes dedicated to finding and tracking NEOs. They've already found and characterised the orbits of over 90% of the truly dangerous objects, the ones a kilometre or larger across, and none of them, not a single one, poses any threat in the foreseeable future. The objects we know about, we can track with precision. We know where they'll be decades or even centuries in advance. If we found one that was going to hit Earth, we'd have years or decades of warning, and we're developing technologies to deflect such objects. The DART mission, which successfully altered the orbit of an asteroid in 2022, proved that we have the capability to change an asteroid's trajectory if needed. What about the objects we haven't found yet? This is where the ongoing survey work is so important. The smaller NEOs, the ones tens to hundreds of metres across, are harder to find because they're dimmer and more numerous. But new telescopes coming online, like the Vera Rubin Observatory, will dramatically accelerate the discovery rate. Within the next decade, we'll probably have found and characterised the orbits of most potentially hazardous objects larger than about 30 metres across. The universe contains dangers, that's true. But they're dangers we can understand, track, and potentially mitigate. The real threats aren't mysterious visitors from interstellar space. They're objects from our own solar system, following predictable orbits, and we're learning to keep track of them all. Let's think about the actual numbers, because sometimes statistics can be more comforting than individual anecdotes. When we look at the rate of asteroid impacts on Earth over the past few billion years, and compare that to the current population of known asteroids, we can calculate the odds of a dangerous impact happening in any given year. For truly large impacts, the kind that would cause mass extinction, the statistics are reassuring in their timescales. An asteroid 10 kilometres across or larger, like the one that contributed to the extinction of the dinosaurs 66 million years ago, hits Earth roughly once every 100 million years. That's the kind of event that reshapes the entire biosphere. And it's incredibly rare. Kilometre-sized impacts, which would cause global devastation but not mass extinction, happen roughly once every 500,000 years. That sounds more frequent, and it is, but it's still a geological timescale, not a human one. Modern humans have existed as a species for about 300,000 years, and in that time, there's no clear evidence of any civilization-ending impact. Regional impacts from asteroids 100 to several hundred metres across happen more frequently. The Tunguska event in Siberia in 1908 was probably caused by an asteroid or comet fragment about 50 to 100 metres across that exploded in the atmosphere. It flattened about 2,000 square kilometres of forest, but because it happened in a remote area, nobody was killed. Events like Tunguska probably happen every few hundred to few thousand years. Smaller impacts happen more often, but cause less damage. The Chelyabinsk meteor that exploded over Russia in 2013 was only about 20 metres across. It produced a spectacular fireball and damaged buildings with its shockwave, injuring over 1,000 people from broken glass. But it didn't cause any deaths, and the actual asteroid fragments that survived to hit the ground were relatively small. Even smaller objects hit Earth all the time. Every day, about 100 tons of dust and small particles enter Earth's atmosphere. Most of this burns up harmlessly, creating the meteors we see as shooting stars. Objects a meter or two across enter the atmosphere several times a year, creating bright fireballs but rarely delivering any material to the ground. What these statistics tell us, when we step back and look at them calmly, is that dangerous asteroid impacts are genuinely rare on human timescales. The kind of impact that would threaten modern civilization happens perhaps once every few 100,000 years. And now that we're actively cataloguing and tracking asteroids, we've reduced the uncertainty. We know the big ones aren't going to hit us anytime soon. There's also something worth contemplating about the nature of these threats. They're not mysterious or malicious. They're simply objects following the laws of physics. Asteroids don't aim for Earth. They don't seek us out. They follow their orbits year after year, century after century in predictable patterns. Most of the time, those patterns keep them far from Earth. Occasionally, over vast timescales, orbits shift slightly due to planetary gravitational influences, and an asteroid finds itself on a collision course. But these events unfold over long periods, giving ample time for detection and response. As you continue to relax, breathing slowly and evenly, let's think about what actually makes a space object dangerous. It's not just about size, though size matters enormously. It's about a combination of factors: mass, velocity, composition, and angle of entry into Earth's atmosphere. Mass is obviously important. A larger, more massive object carries more kinetic energy, and when that energy is released in an impact, it causes more damage. An asteroid 1 kilometre across made of solid rock might have a mass of about 2 trillion kilograms. When it hits Earth at typical asteroid velocities of 20 to 30 kilometers per second, the energy released is roughly equivalent to 100,000 megatons of TNT. That's about 2 million times more powerful than the atomic bomb dropped on Hiroshima. But composition matters too. A solid iron asteroid is much denser than a rocky one, so it carries more mass for the same size. It's also more likely to survive passage through the atmosphere intact, delivering all its energy in a single impact rather than breaking apart at high altitude. Rocky asteroids are more fragile and may fragment in the atmosphere, spreading the impact energy over a wider area or even preventing surface impact entirely. Comets present a different kind of threat. They're typically less dense than asteroids, often being more ice than rock, so for the same size they carry less mass and less kinetic energy. But comets can move faster than asteroids, coming in from the outer solar system at velocities that can exceed 50 kilometers per second. That higher velocity means higher kinetic energy, potentially offsetting their lower density. The angle of entry is crucial for smaller objects. An asteroid or comet fragment entering the atmosphere at a steep angle, nearly straight down, will penetrate deeper before it explodes or impacts. An object entering at a shallow angle, grazing the atmosphere, may skip off entirely or break up at higher altitude where the shockwave and heat cause less damage. The Tunguska event appears to have been a relatively shallow entry, which is why the object exploded at an altitude of 5 to 10 kilometers rather than reaching the surface. For the very largest objects, though, these details matter less. A 10-kilometer asteroid is going to cause a mass extinction event regardless of its composition or entry angle. There's simply too much energy involved for anything else to happen. The impact will create a crater hundreds of kilometers across, throw billions of tons of material into the atmosphere, trigger earthquakes and tsunamis, and possibly cause enough cooling from atmospheric dust to collapse ecosystems worldwide. But here's the beautiful thing about our current situation. We know where those large objects are. Every single potentially hazardous asteroid a kilometre or larger in diameter has been found and characterised. Their orbits are known. We can predict their positions decades and centuries into the future, and none of them are on collision courses with Earth. The remaining uncertainty is all in the smaller size ranges, objects 100 to several hundred metres across that could cause regional devastation but not global catastrophe. Objects tens of metres across that might destroy a city if they hit it directly, but are much more likely to hit remote areas or ocean. The survey programs continue, finding more of these smaller objects every year, steadily reducing the population of unknown potential threats. Each discovery makes us slightly safer, not by changing the actual risk, but by moving an object from the category of unknown threat to known, tracked. And determined to be safe, let's take a step back and think about threats on even longer timescales. When we look at Earth's history, written in rocks and fossils, we can see evidence of major impacts. The most famous is the Chicxulub impact 66 million years ago, but it's far from the only one. There's evidence for dozens of large impacts throughout Earth's history, each one leaving its mark in the geological record. Some of these ancient impacts were truly enormous. The Vredefort impact in South Africa, about 2 billion years ago, was probably caused by an asteroid 10 to 15 kilometres across. It created a crater over 300 kilometres in diameter, though erosion has since worn it down. The Sudbury Basin in Canada, formed about 1.85 billion years ago, may have been caused by a comet or asteroid even larger. These ancient impacts remind us that Earth exists in a solar system that contains billions of small bodies, and over geological timescales, some of them inevitably hit us. But they also show us something else. Life persists. After every major impact event, including the one that ended the reign of the dinosaurs, life recovered. New species evolved to fill ecological niches left empty by extinction. The biosphere as a whole proved remarkably resilient. This doesn't mean we should be complacent about asteroid threats. A major impact would be catastrophic for human civilization, even if life as a whole would eventually recover. But it does provide perspective. The universe isn't hostile to life. It's indifferent. It operates according to physical laws that occasionally result in impacts, but also provides the conditions that allow life to arise and flourish between those impacts. Looking forward, the longer the timescale we consider, the more certain it becomes that Earth will experience major impacts again. In the next million years, Earth will almost certainly be hit by several asteroids large enough to cause regional devastation. In the next 100 million years, an extinction-level impact is statistically likely. But these are timescales that dwarf human history, that dwarf the existence of human civilization, that even dwarf the existence of our species. And crucially, we're the first species in Earth's history that might be able to do something about it. We can detect asteroids decades before they hit. We've proven we can alter their trajectories. As our technology advances, our ability to defend against asteroid impacts will only improve. We might be the generation that breaks the pattern, that ensures no future major impact goes unanswered, that protects not just humanity, but the entire biosphere from preventable catastrophe. In the meantime, tonight, tomorrow, next year, the risk from asteroids is vanishingly small. The objects we know about aren't threatening us. The objects we don't know about yet are probably small and would most likely hit remote areas even if they did impact Earth. The statistical chance of a dangerous asteroid hitting a populated area in your lifetime is far lower than countless other risks you accept without thought every day. So as you lie there, feeling your body heavy and relaxed, you can contemplate the vastness of space, the ancient slow dance of objects in our solar system, and know that despite the existence of real cosmic threats, tonight you're safe. The universe continues its patient mathematical motion, and we continue to learn its rhythms, tracking its dangers, and marvelling at its scale. As we move deeper into our exploration, and as your breathing becomes slower and more regular, let's consider some of the more exotic threats that might exist in interstellar space, not asteroids or comets, but much larger objects. Rogue planets, for instance, worlds that don't orbit any star but instead wander through the galaxy alone in the darkness. Astronomers have discovered that rogue planets are probably quite common. When a planetary system is young and chaotic, gravitational interactions between planets can result in one or more being ejected from the system entirely. These orphaned worlds then drift through interstellar space. lit only by the faint glow of distant stars and perhaps the heat of their own internal radioactive decay. Some estimates suggest there might be billions or even trillions of rogue planets in our galaxy. They're incredibly difficult to detect because they emit almost no light, but astronomers have found a few by observing them as they pass in front of distant stars, temporarily blocking the starlight in a microlensing event. These observations have confirmed that rogue planets aren't just theoretical possibilities, they're real and they're out there. Now the question that might occur to you is whether a rogue planet could threaten Earth. Could one of these dark wanderers come barreling through our solar system and cause devastation? The short answer is that it's possible in principle, but the probability is so low as to be essentially zero. Space is vast, and even with billions of rogue planets in the galaxy, they're spread across hundreds of thousands of light years. The probability of a rogue planet passing close enough to our solar system to cause problems is measured on timescales of trillions of years, far longer than the current age of the universe. And even if one did approach our solar system, we'd see it coming. A planet-sized object, even a dark one, exerts significant gravitational influence. Its presence would perturb the orbits of comets in the Oort cloud, potentially sending some of them falling toward the inner solar system. We'd detect these orbital changes decades or centuries before the rogue planet itself arrived. But let's imagine, just as a thought experiment as you drift towards sleep, what would happen if a rogue planet did pass through our solar system? If it stayed in the outer reaches beyond Neptune's orbit, it might not affect Earth at all. The outer planets would shield us, their much larger masses dominating the gravitational dynamics. If the rogue planet passed through the inner solar system, though, it could gravitationally perturb Earth's orbit. The extent of that perturbation would depend on how close the encounter was and how massive the rogue planet was. A relatively distant passage might shift Earth's orbit slightly, changing our distance from the Sun by a small percentage. This could affect global climate over time, but wouldn't be immediately catastrophic. A very close passage could be more dramatic, potentially even ejecting Earth from the solar system entirely, turning us into a rogue planet ourselves. It sounds terrifying when stated baldly like that, but remember the timescales and probabilities. The chance of this happening in the next billion years is extraordinarily low. The chance of it happening in the next million years is essentially zero. And if somehow such an object were approaching, we'd have plenty of warning. There's no scenario where a rogue planet suddenly appears and destroys Earth without notice. The universe doesn't work that way. Gravity makes itself known across vast distances, and massive objects announce their presence through their effects on other objects long before they arrive. Another potential threat from interstellar space, one that operates on longer timescales than rogue planets, but might actually be more likely, is a close encounter with another star. Stars move through the galaxy on their own orbits around the galactic centre, and occasionally their paths bring them close to each other. Our Sun orbits the centre of the Milky Way at a speed of about 220 kilometres per second, taking roughly 225 million years to complete one orbit. Other stars follow their own paths at various speeds and distances from the galactic centre. Sometimes these paths intersect, or at least come close to intersecting, resulting in what astronomers call a stellar close encounter. Close, in this context, is relative. Stars are separated by such vast distances that even a close encounter typically means the stars pass within a few light years of each other, not close enough for any dramatic interactions between the stars themselves, but it can be close enough to affect their planetary systems. The main concern with a stellar close encounter is the Oort cloud. This is the spherical shell of icy objects surrounding our solar system at distances from about 2,000 to 100,000 astronomical units from the Sun. It contains perhaps trillions of comets, most of them in stable orbits that keep them far from the inner solar system. But if another star passes within a few light years of the Sun, its gravitational field can perturb these orbits. Some Oort cloud objects might be pulled toward the passing star, leaving our solar system entirely. Others might have their orbits changed in ways that send them falling inward toward the sun. These incoming comets could, over the following thousands or millions of years, pose impact threats to Earth and the other planets. The good news, if you can call it that, is that stellar close encounters happen on very long timescales. The nearest star to us right now, Proxima Centauri, is over 4 light-years away. It's not on a trajectory that will bring it significantly closer. Calculations suggest that dangerous close encounters, close enough to significantly perturb the Oort cloud, happen roughly once every few tens of millions of years. The last known close encounter was about 70,000 years ago, when a red dwarf star named Schultz's star passed within about 1 light-year of the Sun. That's remarkably close in stellar terms, and it probably did perturb some Oort cloud objects. But 70,000 years later, any comets sent our way by that encounter have long since passed through the inner solar system or been deflected by the outer planets. The next predicted close encounter won't happen for over 1 million years. Gliese 710, a red dwarf currently about 64 light-years away, will pass within about 1.1 light-years of the Sun in about 1.3 million years. This will be closer than Schultz's star, and it will definitely perturb the Oort cloud. But we have over 1 million years to prepare, and by then, hopefully humanity's technological capabilities will be vastly greater than they are now. So stellar close encounters are real threats, but they're threats on timescales that make them essentially irrelevant to anyone alive today or for countless generations into the future. They're part of the natural rhythm of the galaxy, events that happen occasionally as stars pass each other in their eternal orbits. They're worth studying and understanding, but not worth worrying about on any human timescale. Let's think about a different kind of threat from the stars themselves. Not close encounters, but stellar death. Specifically, supernovae, the explosive deaths of massive stars, and whether one could threaten Earth. When a star much more massive than the Sun reaches the end of its life, it explodes in a supernova, an event so bright it can briefly outshine an entire galaxy. The explosion releases an enormous amount of energy, not just as visible light, but across the entire electromagnetic spectrum. It also releases vast numbers of high-energy particles, cosmic rays, that stream out into space at nearly the speed of light. If a supernova occurred close enough to Earth, it could be dangerous. The high-energy radiation and cosmic rays could damage Earth's ozone layer, increasing the amount of ultraviolet radiation reaching the surface. This could harm plant life, damage ecosystems, and potentially cause a mass extinction. The question is, how close is close enough to be dangerous, and are there any stars near us that might go supernova? Scientists estimate that a supernova would need to occur within about 25 to 30 light-years to pose a serious threat to Earth. That's quite close in galactic terms. Beyond that distance, the radiation and cosmic rays would be diluted enough by the vast space they've travelled through that they wouldn't cause major damage. They'd still be detectable. We'd see a very bright new star appear in the sky, but life on Earth would continue unaffected. The reassuring thing is that there are no stars within 30 light-years of us that are candidates for supernova. Massive stars, the only kind that explode as supernovae, are relatively rare, and none of them happen to be in our immediate cosmic neighbourhood. The nearest massive star that will eventually go supernova is probably Spica, in the constellation Virgo, which is about 260 light-years away. When it explodes, which could be any time in the next 10 million years or so, it will be a spectacular sight in our night sky, perhaps bright enough to cast shadows at night, but it won't harm Earth. The star Betelgeuse, the red supergiant marking Orion's shoulder, is another supernova candidate that people sometimes worry about. It's much closer than Spica, only about 550 light-years away, and it shows signs of being near the end of its life. But 550 light-years is still far enough that even when Betelgeuse explodes, Earth will be safe. The supernova will be incredibly bright, possibly visible in daytime, and it will be an astronomical event for the ages. But it won't threaten life on our planet. there is some evidence that supernovae occurring within a few hundred light-years might have influenced Earth's climate and possibly even extinction events in the distant past. Isotopes found in ancient rocks suggest that a nearby supernova may have occurred 2 to 3 million years ago, but the effects were subtle, certainly not catastrophic enough to leave obvious marks in the fossil record. Looking forward, the probability of a dangerous supernova occurring in the next million years is low. The stars that could go supernova are all far enough away, and a stellar evolution happens slowly enough that we'd have thousands or millions of years of warning as we watched a star evolve toward its explosive end. It's not something that could happen suddenly and without notice. So as you lie there, feeling your eyelids grow heavy, you can let go of any concern about supernovae. The stars near us are stable. They'll shine steadily for millions or billions of years to come. The massive stars that will eventually explode are far away, their death spectacular but harmless to us. The universe is vast enough that even events as energetic as supernovae rarely threaten worlds orbiting distant stars. There's one more stellar threat worth discussing, perhaps the most energetic events in the universe since the Big Bang itself. These are gamma-ray bursts, or GRBS, brief but incredibly intense flashes of high-energy radiation that occasionally appear in the sky from distant galaxies. Gamma-ray bursts come in two varieties. Short bursts, lasting less than 2 seconds, are thought to be caused by the merger of two neutron stars, the incredibly dense remnants of supernova explosions. Long bursts, lasting from a few seconds to several minutes, are thought to come from a specific type of supernova called a collapsar, where the core of a massive rotating star collapses directly into a black hole. What makes gamma-ray bursts so remarkable, and potentially dangerous, is that they concentrate a supernova's worth of energy into narrow beams along the star's rotation axis. If you're unlucky enough to be in one of those beams, you're exposed to an incredible amount of high-energy radiation. A gamma-ray burst occurring in our galaxy and pointed at Earth could be far more dangerous than a nearby supernova. The good news is that gamma-ray bursts are rare. The long-duration bursts require very specific conditions, a rapidly rotating massive star with particular metallicity characteristics. These conditions are more common in the early universe than they are now, which is why most detected gamma-ray bursts come from galaxies billions of light-years away. In our own galaxy, with its relatively high metal content and older stellar population, long-duration gamma-ray bursts are probably extremely rare, occurring perhaps once every million years or less. Short gamma-ray bursts from neutron star mergers are even rarer in any given galaxy, and the probability of one occurring close enough to Earth to be dangerous is vanishingly small. Astronomers have been able to identify some of the systems in our galaxy that might eventually produce gamma-ray bursts, and none of them are close enough or oriented correctly to threaten Earth. The most commonly cited candidate is a star system called WR104, about 8,000 light-years away. It's a Wolf-Rayet star, an advanced stage of massive stellar evolution, and it's rotating rapidly. When it eventually explodes, it might produce a gamma-ray burst. But 8,000 light-years is far enough that even if the burst were pointed directly at us, which is unlikely, the effects would be minimal. We might experience some increase in cosmic ray exposure, but nothing catastrophic. The real danger from gamma-ray bursts, if there is one, is from events we can't predict. An unknown neutron star binary might exist somewhere in our galaxy, hidden from our telescopes, and could merge with its beam pointed at Earth. But the probability of this happening in any given year, or even any given million years, is extremely low. The galaxy is vast and we're a small target. Interestingly, some scientists have proposed that gamma-ray bursts might have been responsible for extinction events in Earth's past. The Ordovician mass extinction about 445 million years ago, which killed off perhaps 85% of marine species, has been tentatively linked to a gamma-ray burst based on timing and other circumstantial evidence. But this connection remains speculative, and even if true, It would represent an event that happens on timescales of hundreds of millions of years. So gamma-ray bursts join the list of cosmic threats that are real, theoretically possible, but so improbable on human timescales that they're not worth worrying about. The universe contains dangerous phenomena, but it's also so vast that the dangerous phenomena rarely intersect with our small world. We exist in a relatively safe pocket of space, orbiting a stable star, with no nearby stellar time bombs waiting to go off. As we continue this gentle drift through cosmic threats and the mathematics that make them improbable, it's worth thinking about why Earth seems to occupy such a safe position in the galaxy. There's a concept in astronomy called the Galactic Habitability Zone, which refers to the region of the galaxy where conditions are most favourable for the development and persistence of life. The Milky Way is a spiral galaxy about 100,000 light-years across, containing somewhere between 200 and 400 billion stars. But not all regions of the galaxy are equally hospitable to life. The central bulge, where stars are densely packed, experiences frequent supernova and high radiation levels. The outer reaches of the galactic disk are poor in heavy elements, making it difficult for terrestrial planets to form. Earth orbits a star in what's sometimes called the Galactic Goldilocks zone, about 26,000 light-years from the galactic centre. Here, stars are spaced far enough apart that close encounters and supernovae are rare, but the region is rich enough in heavy elements that rocky planets can form. We're also positioned between spiral arms, which is significant because spiral arms are regions of active star formation, with many massive young stars that will quickly go supernova. Our Sun does pass through spiral arms periodically as it orbits the galactic centre. The period of these passages is about 100 million years or so, and some scientists have speculated that they might correlate with mass extinction events on Earth. The idea is that passing through a spiral arm increases exposure to supernovae and cosmic rays, potentially stressing the biosphere. But this connection remains controversial, and even if real, it's clearly not strong enough to prevent life from flourishing on Earth over billions of years. The solar system's position in the galaxy also protects us from one of the more exotic cosmic threats, wandering black holes. When massive stars go supernova, they sometimes leave behind black holes as remnants. These stellar mass black holes, typically a few to a few dozen times the mass of the Sun, can be ejected from their birth location and wander through the galaxy. A close encounter with a wandering black hole could be catastrophic, potentially disrupting planetary orbits throughout a star system. But space is so vast, and black holes are so relatively small and rare, that the probability of such an encounter is negligible. There are estimated to be about 100 million stellar mass black holes in our galaxy, which sounds like a lot until you remember that they're distributed across hundreds of thousands of light-years. The average distance between black holes is measured in hundreds of light-years, and most of them are moving relatively slowly compared to the size of the galaxy. What all of this suggests, as your muscles relax further and your mind drifts, is that Earth exists in a remarkably safe location. We're far enough from the galactic centre to avoid most catastrophic events, but close enough to have access to the heavy elements necessary for life. We orbit a stable, long-lived star with no stellar companions that might perturb planetary orbits. We're not in a particularly dense region of space where stellar encounters would be common. And we've existed in this relatively safe configuration for billions of years, long enough for life to arise, evolve and develop intelligence. This doesn't mean we're perfectly safe. As we've discussed, there are real threats from asteroids, very low probability threats from stellar encounters and supernovae, and even lower probability threats from more exotic phenomena. But the universe has arranged itself, through nothing more than the statistics of stellar distribution and galactic structure, to give us a relatively peaceful corner of space where life can flourish largely undisturbed by cosmic catastrophes. It's a comforting thought that the galaxy has habitable zones just as stars do, regions where the conditions are right not just for planets to form, but for life to persist over geological timescales. And we happen to be in one of those zones, not through any special privilege, but simply through the accident of where and when our solar system formed. Now that we've explored the various cosmic threats that exist, from nearby asteroids to distant gamma-ray bursts, let's think about what it means to live with these extraordinarily long odds. How do we contemplate threats that are real, but so improbable that they might as well be impossible on any timescale we can personally comprehend? This is a question that extends beyond astronomy. Life is full of low-probability events, some dangerous, some wonderful. You're more likely to be struck by lightning than to win a lottery jackpot, but both events do happen to someone occasionally. You're far more likely to be killed in a car accident than by an asteroid impact. Yet we drive cars without constant fear while occasionally worrying about rocks from space. The human mind isn't particularly well suited to evaluating very low probabilities. We tend to treat anything with a probability below a certain threshold as if it's impossible, while occasionally fixating on rare events that capture our imagination. This is probably an adaptive trait in most circumstances. Worrying constantly about extremely unlikely events would be paralyzing and counterproductive, but it can lead to distorted perceptions of risk. When people learn that asteroid impacts are possible, they sometimes become concerned. Even though the annual probability of a catastrophic impact is far lower than countless risks they accept without thought. When people hear about interstellar objects entering our solar system, they sometimes imagine these as potential threats, even though the mathematics clearly shows they're not. Perhaps there's wisdom in acknowledging these threats intellectually while not letting them affect our emotional state. Yes, a large asteroid could hit Earth. It's physically possible. But it's not going to happen tomorrow, or next year, or probably in the next 1,000 years. We can know this with high confidence because of physics and mathematics. The universe operates according to rules, and those rules allow us to predict future events with reasonable accuracy. There's something almost meditative about this realization. The future is uncertain in many ways. We don't know what technological advances await us, what social changes will occur, what personal experiences we'll have. But certain aspects of the future are constrained by physical law. The sun will rise tomorrow because Earth rotates and won't suddenly stop. The planets will continue their orbits because gravity works the same way it's always worked. The asteroids we've catalogued will follow their predicted paths because they have no choice but to obey the laws of motion. This doesn't eliminate all uncertainty, of course. There are still asteroids we haven't found. There are quantum effects that make the universe inherently probabilistic at small scales. There's chaos theory, which tells us that some systems are so sensitive to initial conditions that long-term prediction becomes effectively impossible. But even chaos operates within boundaries set by physical law. When it comes to cosmic threats, we can estimate probabilities based on observed populations of objects and events. We might not know exactly when the next major asteroid impact will occur, but we can say with confidence that it's unlikely to happen in the next 10,000 years, probably won't happen in the next million years, and is virtually certain to happen eventually on timescales of tens of millions of years or longer. These long odds, these vast timescales, they give us permission to rest. Not to ignore the threats entirely, we should continue to search for asteroids and study supernovae and understand the galaxy we live in. But to rest in the knowledge that tonight, tomorrow, for all the nights and days of our lives and our children's lives and many generations beyond, the sky above us is not falling. The universe continues its ancient motions, patient and indifferent, neither threatening nor protecting us, simply being. While we're contemplating these cosmic threats and their low probabilities, it's worth considering what humanity is actually doing to address them, because we're not simply passive observers of the universe. We're developing capabilities to detect, track, and potentially mitigate some of these threats. The most advanced efforts focus on near-Earth asteroids, which makes sense because they're the most immediate threat, though still quite unlikely on any given year. Multiple organisations around the world operate telescope systems dedicated to finding and tracking NEOs. NASA's Near-Earth Object Observations Program coordinates much of this work, but there are also significant contributions from the European Space Agency, Japanese Space Agency JAXA, and numerous university and private observatories. These survey programs have made remarkable progress. In the year 2000, we knew of fewer than 1,000 near-Earth asteroids. Today, we've catalogued over 30,000. Most of these are small, only tens of meters across, but the catalogue also includes all the large, potentially hazardous asteroids. The ones that could cause global catastrophe if they hit Earth, we know where they are, and we know they're not going to hit us anytime soon. New telescopes coming online will accelerate this progress dramatically. The Vera Rubin Observatory in Chile, scheduled to begin full operations in the next few years, will survey the entire visible sky every few nights, detecting millions of celestial objects, including many more asteroids. Within a decade, we should have found and characterized essentially all asteroids larger than 140 meters across that come anywhere near Earth's orbit. But finding asteroids is only the first step. We also need to be able to do something about them if we find one on a collision course. This is where planetary defense comes in. The DART mission, Double Asteroid Redirection Test, which flew in 2022, successfully demonstrated that we can change an asteroid's orbit. DART was a spacecraft that deliberately crashed into a small asteroid moon called Dimorphos, orbiting a larger asteroid called Didymos. Neither asteroid posed any threat to Earth. This was purely a test. The impact changed Dimorphos's orbital period around Didymos by several minutes. A small change in absolute terms, but enough to demonstrate that the technique works. By hitting an asteroid with a spacecraft travelling at high speed, we can transfer momentum and alter its trajectory. For a large asteroid detected decades before a potential impact, a small deflection is all that's needed. Change its velocity by just a few centimeters per second, and over the course of years or decades, that translates into the asteroid missing Earth by thousands or millions of kilometers. You don't need to destroy the asteroid or move it dramatically. You just need to ensure that when Earth and the asteroid reach the same point in space, they do so at different times. There are other techniques under consideration as well. A gravity tractor, where a spacecraft parks near an asteroid and uses its own gravitational field to slowly pull the asteroid off course. Nuclear deflection, where a nuclear device is detonated near, not on, an asteroid to vaporize surface material and create thrust. Even painting one side of an asteroid white to change how much solar radiation it absorbs, subtly altering its trajectory over long periods. All of these techniques require one thing: time. The earlier we detect a potentially hazardous asteroid, the easier it is to deflect. This is why the survey programs are so important. They're buying us time, decades or even centuries of warning for any future impact threat. And what about the other threats we've discussed? The stellar close encounters, the supernovae, the gamma-ray bursts. Honestly, there's not much we can do about those with current technology. But they're also far less likely than asteroid impacts, and they operate on such long timescales that our capabilities might be radically different by the time they become relevant. In the very long term, far future humanity, if we survive that long, might have capabilities we can barely imagine. Perhaps we'll be able to detect stellar close encounters millions of years in advance and take protective measures. Perhaps we'll have spread across multiple star systems, making us resilient to any single catastrophic event. Perhaps we'll have technologies for manipulating space-time or energy on scales that seem like science fiction today. But for now, in the early 21st century, we're doing what we can. We're finding and tracking asteroids. We're testing deflection techniques. We're building a catalogue of cosmic threats and learning to predict when and how they might affect us. It's not perfect protection, but it's far more than any previous generation of humans had. We're the first humans who can look at the sky and do more than wonder about threats from space. We can actually find them, track them, and potentially do something about them. As your breathing continues to slow, deep and regular, let's think more broadly about what we mean when we talk about existential risks. An existential risk is something that could end human civilization or cause human extinction. Cosmic threats like large asteroid impacts or nearby supernovae fall into this category, but they're far from the only existential risks we face. Some philosophers and scientists who study existential risk argue that we should be more concerned about risks we might create ourselves than about cosmic threats. Artificial intelligence that becomes uncontrollable, engineered pandemics, nuclear war, runaway climate change. These are risks that could plausibly threaten civilization on timescales of years or decades, not millions of years. This doesn't mean cosmic threats are unimportant, but it does provide perspective. When we think about existential risks holistically, the threats from space that we've spent this evening discussing actually rank fairly low in terms of probability over the next century or millennium. They're important to understand and mitigate where possible, but they're not the most pressing dangers humanity faces. There's something profound in this realization. The universe, despite containing gamma-ray bursts and supernovae and wandering black holes, is actually relatively benign to life that manages to get started. The real threats to civilization are more likely to come from ourselves, from our technologies and conflicts and failure to cooperate on global challenges. This shifts the focus from looking outward at cosmic threats to looking inward at human behavior and societal organization. How do we build resilient civilizations that can withstand shocks? How do we develop technologies responsibly? How do we cooperate globally on challenges that affect all of humanity? These are questions without easy answers, but they're probably more relevant to human survival than worrying about interstellar objects or supernova. Yet there's value in studying cosmic threats anyway, partly because some of them, particularly asteroid impacts, are preventable with current or near-future technology, but also because thinking about cosmic threats gives us perspective on our place in the universe. It reminds us that Earth is a small world in a vast cosmos, that we're subject to physical laws we didn't create and can't change, that our existence is contingent on conditions remaining favourable. This perspective can be humbling, but it can also be unifying. When we contemplate threats that affect all of humanity equally, threats that don't respect borders or ideologies or any human distinctions, it becomes easier to see ourselves as one species sharing one planet. An asteroid doesn't care about nationality or religion or economic system. A supernova's radiation affects everyone equally. These are problems that require global cooperation to address, and thinking about them might help us develop the habits of cooperation we'll need for other global challenges. There's also something valuable in acknowledging that some risks are beyond our control, at least with current technology. We can't prevent a supernova or a gamma-ray burst. We can only observe, understand, and adapt as best we can. This acceptance of limits, this recognition that some things are simply beyond human power, might be healthy psychologically. It can reduce anxiety about things we can't control and focus our energy on things we can. And ultimately, thinking about cosmic threats reminds us of the preciousness and fragility of life. Earth is the only place in the universe where we know for certain that life exists. It might be common throughout the galaxy, or it might be vanishingly rare. We don't know yet. But we know it exists here, and we know it's vulnerable to disruption from various causes, both cosmic and human-caused. This should inspire us to protect and preserve the biosphere, not just for human benefit, but for its own sake. Life has persisted on Earth for nearly 4 billion years, surviving multiple mass extinctions and countless smaller catastrophes. It's shown remarkable resilience, but it's not invulnerable. We have the power to damage it significantly. And we have the knowledge to understand and potentially mitigate some of the cosmic threats to it. With that power and knowledge comes responsibility. Let's think about time itself for a while, as you continue to relax, as your mind drifts peacefully. We've been discussing threats on various timescales, from years to millions of years to billions of years. But what do these timescales really mean? How can we comprehend time periods so vast they dwarf human history? One way to think about it is through analogy. Imagine that the entire history of Earth, about 4.54 billion years, is compressed into a single year. On this scale, Earth forms on January 1st. The first life appears sometime in February. Complex multicellular life doesn't emerge until November. Dinosaurs appear in mid-December and go extinct on December 26th. All of human history, from the first anatomically modern humans to the present day, fits into the last few minutes before midnight on December 31st. On this scale, the time between major asteroid impacts that we've been discussing, hundreds of thousands to millions of years, is measured in hours or days. The time until the next stellar close encounter, over 1 million years, is about 2 months on the compressed calendar. These are still long periods, longer than human civilization, but they're not the vast eternities they might seem when expressed in raw numbers. Another way to think about time is in terms of generations. A human generation is roughly 25 to 30 years, the time between the birth of parents and the birth of their children. In the last 1 million years, there have been about 33,000 to 40,000 human generations. That sounds like a lot, and it is. But remember that the probability of a catastrophic asteroid impact in any given million-year period is fairly low. If we think forward 30,000 generations, which is about as far back as we've come since the last ice age, will humanity still exist? Will we still be recognizably human, or will we have evolved or modified ourselves into something different? Will we still live on Earth, or will we have spread to other worlds? These questions are impossible to answer, but they highlight how absurd it is to worry personally about threats on these timescales. The universe operates on scales that are fundamentally inhuman. Stars live for millions or billions of years. Galaxies evolve over billions of years. The universe itself is nearly 14 billion years old and will likely exist in some form for trillions or even quadrillions of years into the future. Against these scales, human life is vanishingly brief. Your lifetime, 70 or 80 or 90 years if you're fortunate, is less than 1 billionth of the age of the universe. This could be seen as depressing, this cosmic insignificance, but it can also be liberating. The universe will continue long after we're gone, following its laws, indifferent to our existence. This means we're free to live our lives without cosmic responsibility. We don't need to solve the heat death of the universe. We don't need to prevent all possible future catastrophes. We just need to live, to find meaning and joy and connection in our brief time of consciousness. And yet, paradoxically, this cosmic perspective can also inspire us to act. Precisely because the universe is so vast and indifferent, life and intelligence might be rare and precious. We might be one of the only places in the observable universe where matter has organized itself into patterns complex enough to contemplate its own existence. If that's true, or even if it's not, we have a kind of cosmic duty to persist, to learn, to understand the universe we inhabit. This is where thinking about cosmic threats comes full circle. We study asteroids and supernovae and stellar encounters, not because they're immediate dangers, but because they're part of the universe we're trying to understand. And by understanding them, we gain both knowledge and capability. We learn how solar systems form, how matter behaves under extreme conditions, how gravity shapes the cosmos over vast time periods, and we develop the ability to protect ourselves from at least some cosmic threats, in a sense. By worrying about asteroids enough to find and track them, we've transformed them from unknowable threats to known, managed risks. We've taken a piece of cosmic chaos and imposed human order on it, not by changing the asteroids themselves, but by changing our knowledge of them. And in that act of observation and calculation, we've made the universe slightly less dangerous for future generations. As we approach the end of this fourth act, and as your body grows heavier and your thoughts slower, let's engage in some contemplation about alternative histories. What if Earth had been hit by a major asteroid at a different point in history? How might life on our planet be different? The Chicxulub impact 66 million years ago, which contributed to the extinction of the dinosaurs, is the most famous example. But what if it hadn't happened? The dinosaurs had dominated terrestrial ecosystems for over 160 million years. There's no particular reason to think they were about to go extinct on their own. Without the impact, or possibly without the combination of the impact and other stresses like volcanic eruptions, non-avian dinosaurs might still be the dominant large animals on Earth. In that alternative timeline, mammals would likely still exist, but we'd still be small, mostly nocturnal creatures, filling ecological niches the dinosaurs didn't occupy. There would be no humans, no primates, no large mammals at all. Earth would be a dinosaur planet, and depending on how intelligence evolved, if it did, the species contemplating the cosmos might be descended from raptors or sauropods rather than apes. Or consider an alternative where a major impact occurred more recently, say 5 million years ago. After the human lineage had split from other apes but before modern humans evolved, would our ancestors have survived such a catastrophe? Would intelligence still have evolved in whatever species made it through the extinction bottleneck? The path to human intelligence involved many contingent factors, and it's entirely possible that a different catastrophe at a different time would have prevented our existence entirely. We could go the other direction as well. What if a major impact occurred tomorrow? Even with all our technology, a 10-kilometre asteroid hitting Earth would be catastrophic for human civilization. Most humans would probably die from the immediate effects and the following climate disruption, but some would survive in regions less affected by the impact and its aftermath, and those survivors would carry with them knowledge of science, agriculture, metallurgy, all the accumulated learning of civilization. Recovery would be difficult, perhaps taking centuries or millennia, but humanity would likely persist. We're too geographically distributed, too adaptable, too knowledgeable to be completely extinguished by anything short of Earth's complete destruction. And once recovered, that future humanity would have learned a harsh lesson about the importance of planetary defense. They would almost certainly develop more robust systems for detecting and deflecting asteroids. These thought experiments reveal something important about life and intelligence. They're resilient but also contingent. Evolution proceeds down paths determined partly by adaptation to environment and partly by random chance. Major catastrophes like asteroid impacts reshape ecosystems so dramatically that evolution must essentially start over in many niches. This creates opportunities for new forms to emerge. But it also means that the specific forms that do emerge depend on what survived the catastrophe. Life on Earth could have taken many different paths. If conditions had been slightly different, if catastrophes had occurred at different times or not at all, the planet might be dominated by completely different organisms. There's nothing inevitable about humans, about mammals, about any particular form of life. We exist because a specific sequence of events, including both gradual evolution and sudden catastrophes, happen to unfold in a particular way. This realization is both humbling and awe-inspiring. We're products of cosmic chance, living on a planet that's been struck by asteroids, buffeted by climate changes, and subjected to countless other stresses over billions of years. And yet here we are, conscious, intelligent, capable of understanding our own origins and contemplating our place in the universe. The interstellar objects we started this evening discussing, Oumuamua and Comet Borisov, and 3I/Atlas, they're part of this same cosmic story. They're debris from other planetary systems, perhaps systems where life arose and evolved along completely different paths, or perhaps systems where conditions never became suitable for life at all. Each interstellar object is a messenger from another chapter of the galaxy's history, bringing information about how planetary systems form and evolve and sometimes eject their building blocks into the void. In contemplating these objects, in understanding why they don't threaten us while acknowledging that other cosmic phenomena might, eventually on vast timescales, we're engaging with the fundamental nature of existence. We're recognizing our place in a universe that's mostly indifferent to us, but which has nonetheless provided the conditions necessary for us to exist. And we're accepting responsibility for our own survival, using intelligence and technology to protect ourselves from preventable catastrophes, while accepting that some things remain beyond our control. We're entering the final act of our journey now, and your body should be deeply relaxed, your breathing slow and steady, your mind drifting peacefully between waking and sleep. Let's think about the interstellar medium not as a threatening void, but as a kind of ecosystem, a vast environment that shapes and hosts countless objects on their long journeys between the stars. The space between stars is often described as empty, but as we discussed earlier, it's far from truly empty. It's filled with gas, mostly hydrogen and helium, at incredibly low densities. There are clouds of molecular gas where new stars are forming. There are regions of hot, ionized plasma heated by supernova explosions. There are magnetic fields threading through space, guiding the flow of charged particles. There are dust grains, tiny particles of carbon and silicon compounds that scatter starlight and catalyze chemical reactions. This interstellar medium is where all the interstellar objects we've discussed spend most of their existence. Oumuamua is out there now, about 6 billion kilometers from the Sun, and getting farther every day, moving at about 26 kilometers per second. In a few centuries, it will leave the influence of our solar system entirely and return to true interstellar space. The space between the stars where it spent millions or billions of years before its brief visit to our neighbourhood. Comet Borisov is following a similar path, though moving somewhat slower. It's already too far away for even our most powerful telescopes to observe, a faint point of light lost among the background stars. In 1,000 years it will be light years away, frozen solid again, its brief period of activity as it passed near the Sun, a distant memory recorded in scientific papers but unknown to the comet itself. And 3I/Atlas, moving more sedately than the others, will nonetheless eventually leave our solar system and return to interstellar space. It might be 1,000,000 years before it encounters another star, before it feels the warmth of stellar radiation again. Or it might be 10 million years. Time passes differently for objects in the interstellar space, where there's no day or night, no seasons, no change except the infinitesimally slow erosion from cosmic rays and the occasional collision with a dust grain. But this long, cold journey isn't meaningless. The interstellar medium is where much of galactic chemistry happens. Inside dense molecular clouds, where gas and dust are shielded from harsh stellar radiation, complex molecules can form. Astronomers have detected over 200 different molecular species in interstellar space, including organic compounds like amino acids, the building blocks of proteins. These molecules form on the surfaces of dust grains, where atoms can meet and react. Over millions of years, the grains can accumulate thick mantles of ice, water ice mixed with frozen carbon monoxide, ammonia, methanol, and more complex organics. When these ice-covered dust grains are incorporated into comets during planetary system formation, they carry interstellar chemistry into the new system. The water on Earth, the organic compounds that may have contributed to the origin of life, they came from interstellar space, delivered by comets and asteroids early in our planet's history. So the interstellar medium isn't just empty space that objects pass through. It's a factory where the building blocks of worlds and life are assembled, one atom at a time, over eons. Every interstellar object is a product of this factory, carrying in its composition clues about the conditions where it formed and the conditions it passed through during its journey. When we look up at the night sky and see the dark spaces between stars, we're looking at the medium through which these objects travel. We're looking at a vast ocean of gas and dust, lit occasionally by starlight or by the fluorescent glow of excited hydrogen atoms, but mostly dark, mostly cold, mostly empty by human standards, but nonetheless full of subtle activity on molecular scales. This ocean connects all the stars in the galaxy, material expelled from one star, whether through gentle stellar winds or violent supernova explosions. mixes into the interstellar medium and eventually becomes incorporated into new stars and planetary systems. We're made of material that once drifted through interstellar space, that was processed inside ancient stars that exploded before our sun formed. Every atom in your body has a history that spans billions of years and light years of space. Imagine for a moment, as your thoughts grow slower and your awareness softer, that you could ride along with one of these interstellar objects. You're on Oumuamua's tumbling surface, looking back at the solar system as it recedes behind you. The sun, which briefly lit and warmed Oumuamua's surface during its passage through the inner solar system, is now just one bright star among many. At your current distance, about 6 billion kilometres, the sun is still the brightest star in the sky, but it no longer looks like a disk. It's a point of light, brilliant certainly, but no different in appearance from dozens of other stars scattered across the celestial sphere. Earth, if you could see it at all, would be an invisible speck of light lost in the sun's glare. But you're moving away at 26 kilometres per second. Every second, you're 26 kilometres farther from the sun. Every hour, 94,000 kilometres. Every day, over 2 million kilometres. It's a speed that seems fast on human scales, but against the vastness of interstellar distances, it's a patient crawl. From your perch on Oumuamua, you can watch the constellations slowly shift. The stars aren't fixed in space. They're all in motion, orbiting the galactic centre at various speeds and distances. Over years and decades and centuries of travel, you would see the patterns of the constellations gradually change as your position, relative to nearby stars, changes. The Big Dipper would slowly distort. Orion would drift apart. New patterns would emerge from stars that were previously too faint or too far to notice. Behind you, the solar system continues its own journey around the galaxy. In the time it takes Oumuamua to travel 1 light year, about 20,000 years at its current speed, the sun will have moved about 100,000 astronomical units in its orbit around the galactic centre. The paths of the sun and Oumuamua are diverging, never to intersect again. The brief gravitational influence they had on each other is fading into insignificance. And ahead of you, if you could somehow see far enough, are the other stars of the galaxy. 200 to 400 billion suns, most of them smaller and dimmer than ours, some of them larger and brighter. They're scattered across a disk 100,000 light-years in diameter, with a bright central bulge and beautiful spiral arms where new stars are constantly being born. You might encounter one of these stars eventually. Computer simulations of Oumuamua's trajectory suggest it will pass relatively close to several stars over the next few million years. Though quote 1 in this context means within a few light years, it's vanishingly unlikely that it will pass close enough to any star to be captured into a new orbit. It will simply continue through the galaxy, one small object among countless trillions, following the trajectory given to it by whatever gravitational interaction ejected it from its home system millions or billions of years ago. From this perspective, on the surface of an interstellar object millions of kilometres from the nearest star, the threats we've been discussing would seem abstract. What does it matter if asteroids occasionally hit planets? What relevance does supernovae have when you're between the stars? The universe from here is peaceful, dark, cold, unchanging except on the longest timescales. But that peace is partly an illusion created by perspective. Even in interstellar space there's activity. Cosmic rays are constantly bombarding Oumuamua's surface, slowly altering its chemistry. Occasionally a dust grain impacts at high velocity, excavating a tiny crater. Over millions of years the surface will be gradually eroded and altered, the object's appearance and composition slowly changing. And eventually, perhaps billions of years in the future, Oumuamua will encounter something that changes its trajectory. Another star's gravitational field might deflect it onto a new path, or it might enter a dense molecular cloud, where drag from gas, however tenuous, might slow it slightly over hundreds of thousands of years, or it might be destroyed in a collision with another interstellar object. both bodies shattering into fragments that continue their separate journeys. As you continue to rest, breathing slowly, let your mind drift over what we've learned from these interstellar visitors. Not just the scientific data, though that's valuable, but the deeper lessons about our place in the universe and the nature of cosmic threats. First, they teach us that the galaxy is more interconnected than we might have imagined. Before we detected Oumuamua, interstellar objects were theoretical. We knew they should exist, but we'd never seen one. Now we know that these objects are probably passing through our solar system regularly, most of them too small or too distant to detect. The stellar systems of the galaxy aren't isolated islands. They're connected by this traffic of ejected debris. This interconnection has implications for the spread of life, if life exists elsewhere. The hypothesis of panspermia, that life might spread between worlds or even between star systems via asteroids and comets, is more plausible if interstellar objects are common. A microbe frozen in ice on an interstellar comet could theoretically survive the journey between stars and seed life on a new world if conditions were right. We don't know if this has ever happened, but the existence of interstellar objects makes it at least possible. Second, these visitors teach us about the universality of physics. Comet Borisov, coming from an entirely different star system, behaved just like comets from our own Oort cloud. It had a nucleus of ice and rock. It developed a coma and tail as it warmed. Its composition was similar to our comets, with water, carbon monoxide, and organic compounds. This suggests that the laws of chemistry and physics that govern comet formation in our solar system apply elsewhere in the galaxy. This universality is reassuring in a way. It means we can understand the broader universe by studying our own cosmic neighbourhood. The principles we discover here about how planets form, how ice and rock behave, how gravity shapes trajectories, these principles apply to planetary systems orbiting stars light years or even millions of light years away. Third, the interstellar visitors teach us about the importance of observation. We only discovered these objects because we were looking for them, because we had telescopes scanning the sky night after night, because we had software that could detect unusual trajectories in the massive data sets these telescopes produce. If we hadn't been looking, Oumuamua would have passed through unnoticed. Comet Borisov would have been just another faint comet, its interstellar origin unknown. This lesson applies more broadly to cosmic threats. We can only protect ourselves from dangers we can detect. This is why the asteroid survey programs are so important, why we continue to build more powerful telescopes, why we develop better algorithms for finding unusual objects. Each improvement in our observational capabilities makes us slightly safer by expanding the envelope of space and time within which we can detect potential threats. Fourth, these objects teach us humility. They remind us that Earth is one small world among countless worlds, that our Sun is one unremarkable star among hundreds of billions, that our galaxy is one among trillions in the observable universe. The interstellar objects passing through our solar system have likely visited or will visit dozens or hundreds of other star systems during their long journeys. To them, if they could somehow be aware, our solar system is just one brief stop in an endless voyage. And finally, perhaps most importantly for tonight's purposes, these interstellar visitors teach us that the universe, while it contains threats, is not hostile. Objects don't enter our solar system with malicious intent. They're simply following trajectories determined by gravity and momentum, trajectories that occasionally bring them near the Sun and Earth. Understanding this helps us maintain perspective. The universe isn't trying to kill us. It's indifferent to our existence. But that indifference is manageable. We can observe, calculate, predict, and when necessary, deflect or avoid. This is the fundamental lesson that allows us to rest peacefully. Yes, there are cosmic threats, but they're understandable, often predictable, and in some cases preventable. They're not mysterious or capricious. They follow rules, and we're learning those rules. With each interstellar visitor we observe, with each asteroid we catalogue, With each supernova we study, we become slightly more cosmically literate, slightly better at reading the universe's subtle warnings about where and when dangers might arise. As we near the end of our journey together, and as sleep grows closer, let's look far into the future. Not just years or decades or even millennia, but millions and billions of years ahead. What cosmic threats await Earth on these vast timescales, and what might they teach us about the nature of existence itself? In about 500 million to 1 billion years, the sun will gradually brighten enough that Earth's oceans will begin to evaporate. This isn't a sudden catastrophe, but a slow transformation lasting millions of years. The increasing solar radiation will drive more water vapour into the atmosphere, and water vapour is a greenhouse gas, leading to a runaway effect. Eventually, Earth will become too hot for liquid water to exist on the surface, and without liquid water, life as we know it will become impossible. This is perhaps the most certain cosmic threat Earth faces, more certain than any asteroid impact or supernova. The sun's gradual brightening is an inevitable consequence of stellar evolution. As hydrogen fuses into helium in the sun's core, the core becomes slightly denser, which increases the temperature and pressure, which increases the fusion rate, which produces more energy. It's a slow feedback loop that will eventually render Earth uninhabitable. But 500 million years is an almost incomprehensible length of time. For perspective, 500 million years ago, the most complex life on Earth was aquatic. Plants hadn't colonized land yet. Vertebrates were primitive jawless fish. The entire evolution of land plants and animals, the rise and fall of dinosaurs, the evolution of mammals and eventually humans, all of that happened in less than 500 million years. Looking forward 500 million years, it's impossible to imagine what Earth or humanity or life might be like, assuming any of them still exist. Certainly if humans do still exist, we'll have long since developed the capability to leave Earth, whether for other planets in our solar system, planets orbiting other stars, or perhaps artificial habitats in space. The threat of Earth becoming uninhabitable would be manageable because we wouldn't be confined to Earth. About 5 billion years from now, the Sun will exhaust the hydrogen in its core and begin to evolve off the main sequence, expanding into a red giant. In this phase, the Sun will swell to enormous size, possibly large enough to engulf Earth's orbit. Even if Earth's orbit isn't directly swallowed, the planet will certainly be incinerated by the intense radiation. This is the ultimate end for Earth as a habitable world. But again, 5 billion years is such a vast time that it's meaningless on human scales. For perspective, 5 billion years ago, Earth had just formed and was still being regularly struck by planetesimals. The entire history of our planet, from its formation to the present, is about 4.54 billion years. An equally long period stretches ahead before the Sun's evolution makes Earth uninhabitable. What about the galaxy itself? Will it remain a safe environment for life over these timescales? The answer is mixed. Star formation will gradually decline as the galaxy's gas is consumed. The rate of supernovae will decrease as the most massive short-lived stars are gone. But the galaxy will also experience dramatic change. In about 4 billion years, the Milky Way and the Andromeda Galaxy, currently approaching each other at about 110 kilometers per second, will collide. This sounds catastrophic, but galactic collisions are surprisingly gentle events for individual stars. Stars are so far apart that actual stellar collisions are rare even when galaxies merge. Instead, the galaxies will pass through each other, their shapes distorted by gravity, eventually merging into a single larger elliptical galaxy. For any planet surviving in the merged galaxy, including potentially Earth if it somehow survives the Sun's red giant phase, the collision will mostly mean a rearranged sky. Different stars will be visible. The galaxy will have a different structure, but life on any particular planet wouldn't be directly affected unless that planet's star system had a close encounter with another system, which is improbable. Looking even farther ahead, tens or hundreds of billions of years, the universe itself will become increasingly empty. Star formation will eventually cease entirely as all the available gas is locked up in stars, white dwarfs, neutron stars, or black holes. The existing stars will slowly die, leaving a universe of stellar remnants growing ever farther apart as cosmic expansion continues. In this far future, trillions of years from now, the cosmic threats we've discussed tonight will all be long past. No more asteroids, because planetary systems will have either been destroyed when their stars died or scattered by gravitational interactions. No more supernovae, because the massive stars capable of going supernova will all be long gone. The universe will be dark, cold, and in a sense safe because there will be nothing left to threaten anything else. This is the heat death of the universe, the final equilibrium state where entropy is maximized and no more change is possible. It's the ultimate answer to all questions about cosmic threats. Eventually there won't be any because there won't be anything left to be threatened or to pose threats. But that's so far in the future, so beyond any timescale relevant to human existence, or even the existence of complex life anywhere in the universe, that it's more philosophical contemplation than practical concern. For us, here and now, the relevant timescale is measured in millions or billions of years at most. And on those timescales, while threats exist, they're manageable, understandable, and in many cases survivable. We've reached the final chapter now, and your breath is slow and deep, your body completely relaxed, your mind drifting on the edge of sleep. Let's spend these last few minutes thinking about what it means to be aware of all this, to be a conscious being capable of contemplating cosmic threats and cosmic timescales. For billions of years, Earth existed without any life capable of understanding its place in the universe. Simple organisms arose and evolved, becoming more complex over vast timescales, but they lived entirely in the present moment, responding to immediate stimuli without awareness of the deep past or distant future. Even as complex nervous systems evolved, even as brains became sophisticated enough to support memory and planning, no organisms contemplated the cosmos. And then, very recently in cosmic terms, something remarkable happened. In the last few tens of thousands of years, humans developed the cognitive capabilities to wonder about the stars, to create myths and stories about the heavens, to notice patterns in celestial motions. We began to ask questions about our place in the universe. In the last few hundred years, we developed scientific methods that could answer some of those questions. We discovered that Earth orbits the Sun, not the reverse. We learned that the stars are distant suns, many with their own planets. We measured the size and age of the universe. We discovered other galaxies, billions of them, stretching away in all directions to the limits of observation. And in the last few decades, we've achieved something extraordinary. We've begun to catalogue the threats around us. We find and track asteroids. We observe supernovae and study their effects. We detect interstellar objects passing through our solar system and calculate their origins and trajectories. We model the future evolution of stars and galaxies. For the first time in Earth's history, there are organisms on this planet that can anticipate cosmic dangers and potentially do something about them. This awareness is a form of privilege, in a sense. Most organisms that have ever lived, and most organisms alive today, exist without any understanding of the cosmos. They live, reproduce, and die without knowing about asteroids or supernovae or the eventual death of the sun. Their ignorance doesn't protect them from these threats, but it does shield them from worry about them. We can't return to that ignorance. Once you know that asteroid impacts are possible, you can't unknow it. Once you understand that the sun will eventually expand and destroy Earth, you carry that knowledge. But perhaps there's a kind of wisdom in how we hold that knowledge. We can acknowledge these threats intellectually without letting them dominate our emotional lives. We can work to mitigate the threats that are preventable while accepting that some things remain beyond our control. We can find a balance between cosmic awareness and everyday existence, between contemplating billions of years and living in the present moment. There's beauty in this awareness too. When you look up at the night sky now, you see more than points of light. You see suns like ours, possibly with planets, possibly with life. You see the vast spaces between stars where objects drift for millions of years. You see a dynamic universe, full of motion and change, governed by physical laws that we're slowly learning to understand. And when an interstellar object like 3I/Atlas appears, when we detect something that has travelled for eons through the darkness between stars, we can appreciate it for what it is. Not a threat, but a messenger, a travelling piece of cosmic history, bringing information about other star systems, about planetary formation, about the processes that shaped our own solar system billions of years ago. The ability to understand all this, to place it in context, to appreciate both the threats and the wonders of the cosmos. This is one of the things that makes human consciousness special. We're part of the universe contemplating itself. We're a way for the cosmos to know itself, to understand its own nature and history. And perhaps that awareness comes with a responsibility, not to worry constantly about cosmic threats, but to cherish the improbable set of circumstances that allowed awareness to arise in the first place, to protect the biosphere that produced us, to preserve knowledge and pass it forward to future generations, to continue exploring and learning and wondering about our place in the vast cosmic story. Tonight, as you drift towards sleep, you can hold all of this lightly. The universe is vast and ancient and will continue long after we're gone. Cosmic threats exist, but they're distant in time and space. Tomorrow the sun will rise, the planets will continue their orbits, asteroids will follow their predictable paths, and you'll wake up safe on a world that has provided a haven for life for billions of years and will continue to do so for millions or billions more. This awareness, this understanding, this ability to contemplate the cosmos and our place in it, this is enough. You don't need to solve the universe's mysteries or prevent all possible futures. You just need to be, to exist, to appreciate the improbable gift of consciousness in an otherwise largely inert cosmos. And for now, you can let go of it all and simply rest. Thank you for staying with me through this long journey. We've travelled together through over 2.5 hours of space, time, and cosmic contemplation. From the first detection of Oumuamua to the far future of the universe itself, we've explored threats and wonders, dangers and beauties, always returning to the same understanding. The universe is vast and we're small, but that smallness doesn't diminish our significance or our right to exist peacefully. We began tonight by asking about 3I/Atlas and why it wasn't the real threat. The answer, as honestly as I can give it, is that no single interstellar object poses any real danger to Earth. These visitors from beyond our solar system are fascinating, valuable for science, worthy of study, but not threatening. They pass through our cosmic neighbourhood following the mathematics of gravity and momentum, here briefly and then gone, silent witnesses to the galaxy's slow evolution. The real threats, as we discovered, are closer to home and far more manageable than they might first appear. Asteroids from our own solar system that occasionally come near Earth, these we can track and potentially deflect. Stellar encounters and supernovae that operate on timescales of millions of years, these we can observe and understand even if we can't prevent them. And the more exotic dangers, rogue planets and gamma-ray bursts and galactic collisions, these are so improbable or so distant in time that they become philosophical contemplations rather than practical concerns. Take a moment now to notice your breath. Don't change it, just notice it. The slow rise and fall of your chest. The cool air entering your nostrils, the warm air leaving. This simple act of breathing connects you to the universe in ways both profound and mundane. Every oxygen atom you're breathing in right now was forged inside a star billions of years ago, expelled into space when that star died, and eventually incorporated into Earth's atmosphere. You're breathing stardust, you're breathing cosmic history. And as you breathe, as your body grows heavier and your thoughts slower, consider that this peaceful moment exists because of a remarkable series of cosmic accidents. Earth formed at the right distance from the Sun for liquid water to exist. Our planet is large enough to hold an atmosphere, but not so large that it became a gas giant. We have a moon, created in a giant impact early in Earth's history, that stabilizes our axial tilt and gives us regular seasons. Jupiter's massive gravity shields us from many comets that might otherwise bombard the inner solar system. All of these factors, and countless others, have combined to create a world where life could arise and flourish. Where simple molecules could combine into more complex ones, where those complex molecules could begin to self-replicate, where self-replicating molecules could evolve into cells, where cells could form multicellular organisms, where those organisms could develop nervous systems and eventually consciousness. The chain of events leading from the Big Bang to you, lying here tonight, listening to these words, is so improbable that it seems almost miraculous. If you enjoyed this slow drift through cosmic space and cosmic time, a like and subscribe helps others find these peaceful explorations, and I'm always curious about your thoughts. Did certain chapters resonate with you? Are there other cosmic phenomena you'd like to explore this way? The comments are a place for our community to continue these conversations, to share wonder and curiosity, and the comfort that comes from understanding. Let your shoulders drop even further now. Let your jaw unclench completely. Let your tongue rest soft against the bottom of your mouth. Let your eyelids grow so heavy that even the thought of opening them seems like too much effort. You're safe here. You're exactly where you need to be. There's nothing you need to do, nowhere you need to go, no problem you need to solve. Just this moment, just this breath, just this gentle descent into sleep. Wherever you are in the world right now, in whatever time zone, whatever climate, whatever circumstances, I hope you found some peace tonight. Maybe you're in a city, with distant sounds of traffic filtering through your windows, the glow of streetlights keeping the darkness at bay. Maybe you're in the countryside, where the night is truly dark, and if you looked outside you might see the Milky Way stretching across the sky. Maybe you're somewhere in between, in suburbs or small towns, where the night is a mixture of human light and natural darkness. Wherever you are, above you, beyond Earth's atmosphere, the cosmos continues. Right now, as you lie there, asteroids are following their orbits with mathematical precision. Comets are slowly approaching or receding from the Sun. The planets continue their ancient dance around our star. And far beyond our solar system, in the depths of interstellar space, objects like Oumuamua and Comet Borisov are travelling through the darkness, moving between stars on journeys that will last for millions of years. I hope your breathing has slowed and deepened. I hope it's become automatic, effortless, each breath requiring no thought or intention. I hope your heartbeat has slowed to its resting pace, steady and reliable, pumping blood through your body without any conscious direction from you. I hope your muscles have released their tension, becoming loose and heavy, sinking into whatever surface supports you. And I hope your thoughts have quieted. Not disappeared entirely perhaps, but softened, become less urgent, less demanding of attention. Thoughts drifting through your mind like clouds across a summer sky, present but not troubling, noticed but not dwelt upon. Or perhaps your thoughts have already faded, and you're in that liminal space between waking and sleeping, where awareness persists but becomes dreamlike, where logic loosens and the mind wanders through associations and images without the constraints of full consciousness. Look up at the stars now, if you can, or imagine them if you can't. Close your eyes and picture the night sky on the clearest night you've ever experienced. Maybe it was during a camping trip far from city lights. Maybe it was on a beach, where the sound of waves mixed with the sight of stars. Maybe it was in a desert, where the air is so dry and clear that the stars seem close enough to touch. Or maybe it's a sky you've only imagined, more beautiful than any real sky could be, with stars in colours you've never seen. Arranged in patterns that feel meaningful even if you don't know why. All those stars scattered across your inner vision, each one is a sun. Most of them are older than ours, born billions of years ago when the galaxy was younger and the universe was filled with the debris of the very first generation of stars. Some are younger, born only millions of years ago in the giant molecular clouds that still exist in the spiral arms of the Milky Way. And a few, just a few, might be forming right now. This very moment, collapsing from clouds of gas and dust into bright new sources of light and heat. Around many of those stars, perhaps most of them, there are planets. Rocky worlds like Earth, scorched by proximity to their suns or frozen by distance. Gas giants like Jupiter, with storms larger than our entire planet raging in their atmospheres for centuries. Ice giants like Neptune, with winds faster than the speed of sound. And perhaps, somewhere among all those planets orbiting all those stars, there are worlds where conditions are right for life. Maybe on some of those worlds life has arisen. Maybe it's simple, single-celled organisms living in oceans or hot springs or deep underground. Maybe it's complex, multicellular, diverse, filling every available niche in the environment. Maybe, just maybe, on some of those worlds, life has developed intelligence, consciousness, the ability to look up at their own skies and wonder about other worlds, other stars, other possibilities, and if such beings exist, if there are other conscious minds somewhere in the galaxy, maybe some of them are doing exactly what you're doing right now. Lying in their equivalent of a bed, in their equivalent of night, thinking about the cosmos and their place in it, contemplating the same questions we've explored tonight, wondering about cosmic threats and cosmic timescales, feeling both infinitely small and somehow significant, participants in the universe's slow awakening to its own existence. It's a comforting thought, in a way, that we might not be alone, that somewhere among the hundreds of billions of stars in our galaxy, among the trillions of galaxies in the observable universe, there might be others who share our capacity for wonder, our curiosity about existence, our ability to contemplate both the beauty and the dangers of the cosmos we inhabit. But even if we are alone, even if Earth is the only place in the entire universe where matter has organized itself into patterns complex enough to ask questions about its own existence, that doesn't diminish the significance of this moment. If anything, it makes it more precious. You are potentially one of the only beings in the entire universe capable of understanding the universe. You're a rare arrangement of atoms that can contemplate other arrangements of atoms. You're a way for the cosmos to know itself, perhaps one of the only ways. All those points of light in your imagined sky, all those stars and the spaces between them, all of it exists whether anyone is observing it or not. The universe was here long before life arose on Earth, and it will continue long after Earth is gone. But right now, in this moment, there's at least one place in the universe where the universe is aware of itself. And you're part of that awareness, your consciousness, your ability to think and wonder and understand. That's one of the most remarkable phenomena in the known cosmos. But you don't need to carry that weight tonight. You don't need to be the universe's consciousness right now. You can let go of awareness, let go of understanding, let go of all the thoughts and ideas we've explored over these past 2.5 hours. You can simply be, without thought or intention, without purpose or goal. Just existing, just breathing, just present in this moment before sleep takes you. There's a beautiful simplicity in that surrender. For hours we've been thinking about vast scales of space and time, about cosmic threats and cosmic wonders, about probabilities and possibilities and distant futures. But now, as sleep approaches, all of that can fade away. The universe will continue without your awareness of it. The stars will keep shining. The planets will keep orbiting. Asteroids will follow their paths. Interstellar objects will drift through the darkness. All of it will continue, whether you're conscious of it or not. And tomorrow, if you choose, you can return to this awareness. You can look up at the sky with new appreciation, new understanding. You can think about the cosmic context we've explored and find comfort in the timescales and probabilities that make catastrophic events so unlikely on human scales. But tonight, you can rest in ignorance, in blissful unconsciousness, in the simple peace of sleep. Let your breath become even slower now, even deeper. Let each exhale last a little longer than the one before. Let your body sink deeper into rest with each breath cycle. Feel the weight of your head against your pillow. Feel the weight of your arms and legs, heavy and still. Feel gravity pulling you down, holding you to Earth's surface, the same gravity that keeps the moon in orbit, that keeps Earth circling the sun, that holds galaxies together and governs the motion of everything in the universe. You're connected to all of it through gravity, through the atoms in your body that were forged in stellar furnaces, through the consciousness that allows you to comprehend your place in the cosmic story. But you're also separate from it, an individual existence with its own experiences and thoughts and feelings. Both things are true simultaneously. You're part of the universe, and you're distinct from it. You're connected to cosmic history spanning billions of years, and you're living in this one moment, this one breath, this one peaceful descent into sleep. The universe is patient. It's been here for nearly 14 billion years. It will be here for trillions or quadrillions more, gradually spreading out, cooling down, evolving toward its final equilibrium state in the unimaginably distant future. It doesn't need you to understand it. It doesn't need you to protect it or save it or even think about it. It simply is, existing according to physical laws that operate whether anyone is watching or not. And you're allowed to simply be as well. Not as a cosmic consciousness contemplating the universe, but as a human being needing rest. Not as an observer of stars and asteroids and interstellar objects, but as a body requiring sleep. Not as a mind full of knowledge about threats and timescales and probabilities, but as a peaceful presence in a quiet moment at the end of a day. So sleep well, wherever you are. Dream of interstellar objects drifting through the darkness, if you dream at all. Dream of galaxies slowly colliding over billions of years. Dream of stars being born in molecular clouds and dying in spectacular explosions. Dream of Oumuamua tumbling through space, moving away from our sun at 26 kilometers per second, heading back into the interstellar medium where it spent millions of years before its brief visit to our solar system. Or don't dream of any of that. Dream of everyday things, of people you know and places you've been. Dream of nonsense that makes perfect sense while you're dreaming, but will fade to confusion if you try to remember it when you wake. Or don't dream at all. Just rest in the deep restorative unconsciousness that your body needs, that your mind needs, that you deserve after 2.5 hours of cosmic contemplation. The mathematics of orbital mechanics guarantee that no asteroid will hit Earth tonight. The timescales of stellar evolution guarantee that no supernova will erupt nearby. The vast distances between stars guarantee that no rogue planet will suddenly appear to disrupt our solar system. 3I/Atlas was never a threat, and the real threats operate on timescales so long that they're irrelevant to your life, to your children's lives, to countless generations, into a future that's difficult to imagine. You're safe. We're safe, at least for tonight and for all the nights of our lives, and for countless generations into a future we can barely comprehend. The universe, despite its occasional violence, despite the existence of asteroids and supernovae and all the other phenomena we've discussed, is a place where life can exist, where consciousness can arise, where you can lie peacefully and drift into sleep without fear of cosmic catastrophe. May your sleep be peaceful and deep. May you wake tomorrow refreshed and ready to experience another day on this rare and precious world. May you carry forward a little of tonight's perspective, a little cosmic understanding to help you navigate whatever challenges tomorrow brings. And may you always remember that you're part of something vast and beautiful, and in its own way, gentle. The universe has been here for billions of years before you were born. It will be here for billions of years after you're gone. But right now, in this moment, you're part of it. You're a way for it to know itself. And that's enough. That's more than enough. That's everything. Good night. Sleep well. Dream peacefully. and know that the cosmos continues its ancient dance, patient and eternal, while you rest safely in your small corner of space and time. Good night.